These are notes for AP Calculus AB. On 5.7, we're going to be discussing applications of differential equations again from the point of acceleration. So I only have 2 problems for you here on this assignment or this set of notes with a couple of questions for number 1. Number 2 is going to be a little bit different. We're going to focus a lot on problems like question number 1 here. So part A is going to have us use integration to find our velocity and position functions, and then they'll ask us some questions about that. And this is going to be the typical type of problem that we'll be working with. So this first problem says a rock is thrown up with an initial velocity of 44 feet per second. So I'm going to make a note right now. Initial velocity of 44 feet per second is telling me that the velocity at time 0 is 44. This is also like being told the constant of integration for the velocity function. You're also told that it's thrown from a height of 6 feet. So this is your starting position. So at time 0, the position S is 6. So at time 0, the velocity is 44. At time 0, the position is 6. So we're going to start with acceleration due to gravity. In feet is negative 32 feet per second. Starting with that value, we will integrate. So integrating each side with respect to time here. So on the left, that's going to get us back to our velocity function, v of t. On the right, negative 32t plus c. So here, we're going to use our initial velocity. So at time 0, when t is 0, the velocity v equals 44. So 44 is equal to negative 32 times 0 plus c, and c is 44. So like I mentioned, initial velocity is also telling us our constant of integration here, right? You have to be really careful with that. That doesn't always work out for you, but as long as you're working with a nice polynomial, it should. So we can write our velocity function now. V of t is equal to negative 32t plus 44. So now that we have our velocity function, we can integrate again to get back to our position function. So integrating each side with respect to time. Integrating velocity gets us back to S, position. On the right, we get negative 16t squared plus 44t plus c. So again, using that initial condition for the position function, at time 0, S equals 6. So 6 is equal to negative 16 times 0 squared plus 44 times 0 plus c, and so c is 6. So we finally have our position function. So S of t is negative 16t squared plus 44t plus 6, and our velocity function is negative 32t plus 44. Those are the 2 equations we were asked to find. So now we're going to use those to answer questions B and C. B asks, what is the maximum height the rock reaches? So remember that our position function follows the path of a quadratic or a parabola. It's a downward facing parabola at that. So we're looking at something that follows this projectile motion path. So the maximum height at the top here, what do we know about a projectile when it reaches that maximum height? It has a velocity of 0. So we're going to take our velocity function and set it equal to 0. So we'll solve that for t, and what this does is tells us the time that it takes the projectile or the rock to reach that maximum height. So this comes out to 1.375 seconds. So that's not the answer to the question, what is the maximum height? So we'd like to know at this time, what is the height of the rock? So we're going to take this time and plug it into our position function S. So S of 1.375. So you'll use your calculators to plug that in, and you'll come up with 36.25. And our answer for position, remember that acceleration is feet per second, velocity is feet per second, position is feet. So that is the height here. Part C, how much time passes before the rock hits the ground? This time we are solving for a time, t, and we just need to start with what do we know about our projectile when it hits the ground. So this is going to be ground level here. And ground level is really just our x-axis. Okay, so we're looking at when our position function is equal to 0. So these are the two cases you'll deal with a lot. Maximum height, velocity is 0. When you hit the ground, your position is 0. You're at ground level. So setting our function equal to 0, if it were a nice quadratic, it might factor, but this one doesn't. So you'll be using your calculators for this one. So we'll want to type in our equation here to our y equals screen. And then we're going to sketch and look for our x-intercepts. Since we're looking for how much time it takes before we hit the ground, we're looking not for when the projectile is thrown up, so starting at that height of 6 feet up here, and that's that y-intercept, but when it comes back down to touch the ground. So this x-intercept, it looks like it's about 3, but using the trace button and typing in 3, I can see that it's not exactly at 3, but just less than that. So to calculate our x-intercept, or 0, we're going to use the calculate feature. So second calc, we're going to use the 0, number 2. Remember the left bound, scroll past it on the left side and hit enter. Your right bound, scroll past it on the right side and hit enter. For a guess, just hit enter one more time, and there's our 0. So t equals 2.8801, and rounding to the thousandths place would just be 2.88 seconds. And that's the answer, since we were looking for that time. So again, that's going to be the most common type of question that you'll be working with in this section. So number 2, it's a little more challenging, and you'll see this every now and then, but this is a good problem to work with. So this is similar to the problems we did in Objective 6, where we started with our second derivative, and we didn't have enough information to find the constant of the derivative. We had to integrate before we knew that part of the problem. So this is going to be very similar to that. All right, so we're going to start here, since we're working in meters with an acceleration due to gravity of negative 9.8 meters per second. We're told that we don't know and need to find the initial velocity. So this is what we don't know. What is the initial velocity? V of 0 equals what? So finding that if we're launching from ground level, so starting at ground level means that our initial position is 0. Time 0, position 0. Remember, when you're on the ground, your position is 0. If you start from ground level, that's at time 0. Your position is 0. We want to reach a maximum height of 1,000 meters. So like we did earlier, maximum height of 1,000 meters, So we're talking about at the very top, when the velocity is 0, we want our position to be 1,000. So we're looking at when velocity equals 0, the position is equal to 1,000. So we'll start back here with our acceleration and start by integrating. So add in your dt here, and you're ready. Integrating acceleration gets us back to velocity. This is negative 9.8 t plus c. So here's where we stop. We don't know the initial velocity. V of 0 equals, we're not sure what value here. So we can just leave it as c, or we can call it something else, since it might be easier to think of it as another value here. I guess I'll just leave it as c for now. And this is the value that we're trying to find. So what is this value here, this constant? Okay, so that's our unknown. Notice if I plug in 0 for t, I get c equals the velocity at that time, and that's what we don't know. So we'll just leave it as c, and we'll continue to integrate. All right, so integrating here, we're going to get back to our position function, s of t equals negative 4.9 t squared. Integrating our constant, so we did this before. If this were a 5, we'd integrate to get 5t. Since it's just an unknown constant value, we'll integrate and get plus ct. And then we're going to have our constant of integration here. So in a previous set of notes, we just went ahead and called it d, so we can do that for now. And we can use the fact that our initial position is equal to 0 to find this value. So when t equals 0, s equals 0. So 0 is equal to 0 plus 0 plus d. So this value is 0 right here. So my position function, s of t, is now negative 4.9 t squared plus ct. And remember, we're solving for c. So in number 1, we started by writing our position and velocity functions. We've basically done the same thing here. My velocity function, right here, v of t equals negative 9.8 t plus c. I've also written my position function, s of t, is equal to negative 4.9 t squared plus ct. What we're going to do is, at the same time, these two things here at the end are happening. When at v equals 0, s equals 1,000. These things are happening at the same time. When v is equal to 0, s is equal to 1,000. What we've done is created a system of equations to solve. So we have an unknown t and an unknown c. You have two equations, two unknowns. It's just a complicated looking system of equations. Okay, so we're trying to find the initial velocity c. I'm going to take my first equation here and solve for t in terms of c. So taking this equation here, you would subtract c and then divide by negative 9.8. So c over 9.8. So the double negative reduces to a positive, and we're left with this, which we're now going to substitute. Remember, a system of equations can be solved by either substitution or the elimination method. Elimination or the addition method won't work here because I don't have like matching values. So instead, we'll use substitution, and we'll replace all the t's here in my secondary equation with c over 9.8. So this is now negative 4.9 times t squared plus c times t and it's equal to 1,000. So our job is to solve for c, and here I have now an equation with c. So remember, c is that unknown initial velocity. It was the constant of my velocity. That's what we're solving for. So nice way to simplify this, negative 4.9 times, we're just going to square the terms in here. So this is now c squared over 9.8 squared. Plus, over here, c times c is also c squared over 9.8 is equal to 1,000. Easiest way to simplify an equation with fractions is to multiply everything by that common denominator. So I'm going to multiply through everywhere by 9.8 squared. So I'm just avoiding having to use my calculator too much by doing this. So if I distribute that to this first term, the 9.8 squared will reduce, and you're left with negative 4.9 c squared. Distributing to the second term, you reduce 1 with the top and the bottom. That leaves you with a 9.8 times c squared. And on the right side, I'm just going to write this right now as 1,000 times 9.8 squared. Because that's what it is. It's just multiplying, and I don't want to use my calculator just yet. On the left side, you have like terms. They're both c squared with different coefficients. Negative 4.9 plus 9.8 is positive 4.9 c squared. And then to solve for c squared, we'll just divide both sides by 4.9. So at this step, I can use my calculator here to get c squared is equal to 19,600. And so c comes out to 140. All right, so now that I have this value, that's all it was asking for. What's the initial velocity? That was my constant of my velocity function. I only need to include my units. So if position is measured in meters and gravity is meters per second, velocity is meters per second. And that's the answer.